Okay, here we are. This is Math 1201. This is the lecture scheduled for Tuesday, November 17, and Wednesday, November 18. If you're in the Monday, Wednesday class and have not had the Monday lecture, you're watching this out of order. So I would recommend those of you in that section wait until Monday after class, 5:15, to watch this, or it may not make too much sense. So in the hopes of making some sense out of this stuff, we're going to try to guide you through some of this. It's my opinion, and it's only an opinion, that they go off in a lot different direction than I'm used to seeing, and it can be considered to be challenging part of this in the beginning of chapter 10 that we get to today. So I'll try to guide you through the part that I consider to be important and gloss over the part that I don't think you will find to be critically important towards the class. But of course, we need to finish up 8.8, which we'd almost finished before, with the two sections in chapter 8 were getting kind of long. Then there's 8.9, a very short summary, which is actually very good, more in the style that I teach in. And then we have 10.0, an introduction to chapter 10, which is about confidence intervals. And then we'll go partway through 10.1, just to kind of stay on pace. And because 10.0, I'm going to glide through a big chunk of it anyway. So that part may look long, but I'm not going to pay as much attention to it. And we'll have more word about the final and chapter quizzes and stuff. We didn't cover much out of chapter 7. I'm not so sure I'm going to do a chapter quiz out of 7. I'm doubtful right now. But let's get to the material so we don't spend too much time. Here we looked at regression lines and scatter plots of the pinky as the x variable versus the middle finger length as the y variable. And then they switched them and made the middle finger length the x variable and the pinky length, your little finger, the y variable. It's the same data, it's just been kind of transformed. It's the same correlation too. They just don't list it here. They list how to build the regression line. That would be like y equals 0.609x plus 10.531 in this particular second graph. And we went through part of this before, and we went through a little bit of that. But where we stopped was that the slopes are different because they've been kind of transformed, but it's the same data. Just depends on how you want to emphasize it. Seems like most data, it's pretty obvious what x and y are, but there are times where you're not really sure. You're just exploring two variables or more in some cases, and you don't know where to sort them. So you just try them both and see what happens. Yeah, so we went through all that. Where we stopped last time was this unstandardized slope, the B1 coefficient. That's the slope, sometimes called M. Should always be interpreted in context, and it does depend on the units of measurement. So correlation does not depend on the units of measurement, but slope does. They're kind of tying them very closely together here, more than I probably would. Anyway, there's a lot going on in a slope, that's true. Just we're trying to do correlation now. And they do relate to each other. They both have the same direction. When they're both positive, they're both headed up. When they're both negative, they're both headed down. But you know, the slope does depend, and you know, the y-intercept does depend on the actual units, and our prediction does depend on the actual units. Is it dollars? Is it people? Is it something else? But the advantage of using the standardized slope, Pearson's R, well, that's not what I would call it. I would call it the correlation coefficient, and it gives you a sense of the strength of the relationship, which does not have units associated with it. And R is the same. They didn't bother to show it to you, but R is the same in both cases. It does not matter how you tie the two variables together, which one's y, which one's x. R doesn't care. R doesn't care even if you clearly get it wrong and kind of force kind of a backwards train of thought. R will still give you the same number. So R is quite flexible and does not have units, so you don't really have to worry about them very much. Okay, so in this particular case, we'd like to look at a couple things here. And here, we just need to look at the hint, and what they're asking us to do is to calculate the correlation of middle by pinky and then pinky by middle. And the hint, well, is there a hint? Just submit the code and see the symmetry. So this bears out what I've been talking about here. Oh, they're both the same. 0.748 to 3 decimal places, or there's 6 decimal places. They're both identical. R does not care what order you put them in. The slope would. So why is the strength the same? As I just said, R does not really pay much attention to that. The standardized slope is the same because now the original units do not matter. That is, R is the same. Both variables are now in terms of the standard deviation. Correlations are an excellent way to gauge the strength of a relationship, and the trade-off is predictions based on correlation sometimes can be difficult to interpret. So anyway, they talk about the connection between R squared and PRE. This PRE is something that isn't really dwelt on in some math classes, but I just look upon it as R squared. That's a measure of correlation. It tends to remove any negative sign that may be on the R. Remember, when it's sloping downwards, you have a negative R, but when you square it, it becomes positive, or perhaps zero if it was originally zero. So this doesn't list R on this ANOVA table, complicated to do, but we do have R squared, otherwise known as the PRE, as they call it, the proportional reduction in error. So try taking the correlation and squaring it in this window. Will we get 0.1529? Well, let's take a look at the hint and see what it says. Use the caret to raise a value to a power. Well, that's no big deal. So I guess all we have to do is just take this correlation they've already kindly done for us and be sure to square it. So really all we have to do is to put a caret and a 2. So that was their hint. It was a good hint. And now we're just simply going to square the correlation. And R squared equaling PRE. They have little r here and capital R there, but whichever, don't worry about that. Let's go ahead and run this and see what happens. Oh, there's a 0.1529, just as they said. And yeah, there's use for that. 1 minus R squared and stuff, but since they're not talking about it, I'm not going to worry about it. It's amount of variability in this, that, and the other thing. So yeah, we usually call this R squared, and they call it PRE, fine. And so it says what percentage of the total variation is explained by the regression model. So how well does the regression model do its job? So it's a way of measuring how well we're doing. And there's a lot to be said for high and low numbers, but that's not exactly my cup of tea, but we'll do it as we need to. I actually have the teacher mode up so you can kind of see the answer to this. Complete the following sentence. If we took a different sample of students, yes, we would almost certainly have gotten a slightly different estimate of the true correlation. Yeah, different samples yield different results nearly always. And the others are wrong. We would not get a different R because the R's are the same, no. We would not get a different R because it would have to be the same as the square root of PRE. No, not really. Now, this one you would not perhaps know. They're annoying statisticians, that is, for many reasons, but maybe not this one. But anyway, because they use so many difficult terms to mean the same thing. Well, difficult's a matter of being, what's your opinion on that? But which are all exactly the same. Well, PRE and R squared, they just said that. Something that I don't remember them talking about at all is eta squared. And yeah, that's like the hurricane that's coming. No, it's an iota. I'm losing track now. But not SS for sure. Okay, so let's go back to settings, and I'm going to get into 8.9, and let's see if we can get to student view so I don't have to tip my hand quite so quickly here, and I can talk around and only hint at the answer instead of just handing it to you so you don't have to do any thinking. So let's see. Let's go to 8.9. This is a very, very quick one. Limitations to keep in mind. And correlation does not imply causation. So just because two things are correlated doesn't mean that one causes the other. It could be a fluke, or it could be that there's really something going on, or maybe Y causes X, or maybe X causes Y. Hard to say. We don't know that for sure, but compiled with many other bits of knowledge, sometimes you can get to that point where you can strongly feel that one does cause the other, such as studying more hours leads to a better grade on average. And yes, that's well known to be true. I wish I could say it was always true for everyone, but there is some random chance involved and certain other factors, but certainly hours of study contributes to a higher, say, average percent in your grade, which would be like a 97 leading to an A, or an 82 leading to a B, things like that. So if you measure it numerically, you could definitely see something there. Okay, they talk about spurious relationships, and we've seen these before. Children's shoe size correlated with scores on an achievement test. The tendency to wear skimpy clothing is correlated with higher temperatures. So in the first case, the shoe size. This correlation is spurious. Age is a confounding variable, that is, age causes increases in shoe size for kids and achievement for most kids, practically all kids. Now, in the case of skimpy clothing, the relationship is real, but the direction must be sensibly interpreted. Hiking up the temperature might cause people to wear less clothing, but taking off clothes is not going to cause the temperatures to go up, no matter how many times you try. So that's not going to work. I used to think that correlation implied causation. Then I took a statistics class. Now I don't. Sounds like the class helped. Well, maybe. That's pretty funny, I think. So anyway. Also, thumb length measured in millimeters is going to be perfectly correlated with thumb length measured in centimeters. That's because they're off by a factor of 10. The points will be perfectly laid on a straight line. But does this get us any closer to understanding anything? No, that's just a matter of style, what units you want. You put it in inches too. What if we find a correlation that makes perfect sense? Say we do a study and find the time spent studying correlates with score on the final exam. Could we present that? Well, yeah, I'd say so, because you do have other bits of knowledge that you just don't throw away. Of course they do. Statistics can help, but you can't get into I don't know, boxing championships with ladies' fashions, as they were trying to correlate 100 years ago. So we don't go there at all. But yeah, if there's something that seems to make sense, then it almost for sure does make sense, and this is one of those. But there are other factors too. There are geniuses that barely study. I've met a couple of people like that. They were gifted, so they would just spend very little time, look it over, and they'd get their A. I can tell you stories, but I better not. And other times people work. I used to work 13, 14 hours a day on one class, and I was lucky to get a D. And it was one of those classes that almost everybody failed. It was very, very tough. So I've seen both extremes on that. But in general, the more you study, the better you do. We have another couple of things to mention. Are all lines straight? Well, the models we consider, they are only linear models. We can fit a straight line. There are other models, though, and I'm not sure about these body mass index numbers. I think they're a little bit low, but anyway, they do say that they've tried to connect a relationship between body weight and risk of death. So maybe this is of a certain, I don't know, I can't interpret this completely. I always thought body index was in the 20s or something. But we can't put a straight line through this. If we put like a flat line through this, we don't get much information. This is one of those parabolic or second degree type of relationships where you'd have to say y equals x squared or something. And yes, of course that exists. That's actually one step removed from what we're talking about. But we're not equipped to talk about it. It is much more difficult than it seems. And plus, linear relationships do quite a good job much of the time. You can get into something like y equals x to the 10th plus something y equals x to the 9th and 8th and 7th. And you can over-explain things, but sometimes you're just wasting your time. And the idea is to try to keep it as simple as possible so it'll be more believable. But if you truly have a complicated relationship, yeah, there is advanced methods, obviously, it can be done. Here, you would have to have something involving a second degree or y equals x squared situation for this. Because clearly in the middle, people have a much less chance of dying. And if you're underweight or overweight, even though these numbers may not be completely true, your chances of dying goes up. So if you ignore the shape of the relationship and overlaid a line, it would be flat, and indicating no linear relationship. Well, that's not what would be called for here, and that's beyond the scope of this class. So before fitting a straight line linear regression model, you go to the relationship, see if it makes sense. If it doesn't, think about a different model. Call the statistician and let them do it. Working for the Forest Service, they had statisticians and even a mathematician. And they basically set their own hours. They were basically their own bosses. And that's why sometimes those jobs are considered quite desirable. Why is this woman scowling at me? Do I know her? If she loves you more and more each day, by linear regression, she hated you before you met. As you go back in time, she hated you more and more and more. So is that pertinent? Don't think so. I guess it's possible, but probably not. So Problem of extrapolation. So yeah, you just can't get to that kind of a thing. Do regression lines go on forever? No, they start at a particular spot, meaningful spot, and they sometimes end at a meaningful ending too. And you go outside that range, and sometimes you lose meaning completely. So extrapolation, we talk a little bit about that. Somebody who might be 0 inches tall is predicted to have a thumb length of -3 millimeters. No, don't think so. So usually it's just in an acceptable range of data. They do have, in fact, while I'm thinking of it, well, that's in the prior section, but you can say that sometimes it'll only work for a middle group, and then you kind of exclude the beginning, exclude the ending. That's certainly fine. Come up with something you learned in the last 2 sections of Chapter 8. And now we have kind of this doesn't affect your grade at all. It's more of a survey. I think they're more interested than I am, frankly, about your feelings about your course. And these are the sentences that you may agree or disagree with. No right or wrong answers. I know I can learn the material in the course from disagree to agree. I think I can be successful. Let's see. This content is important to me. When I learn, will be useful in the future. I'm unable to put the time in. I have to give up too much to do well. This course is too stressful for me. Well, I would I would say yes. I'm not supposed to, but yeah, it's been a bit stressful for me too, and that's because I've taught it basically a very similar way for a long time, and this is rather different for me. So I'm doing the best I can to get through it, and the statistics part I'm fine with. It's the R stuff that sometimes gets a little bit weird, and their interpretation and in psychology, they just see things differently than we do in math. So let's go ahead and get back to Chapter 10. So I have to get into Chapter 10 first. I've opened up everything. In fact, I've even opened up Chapter 9. And I don't know if you're going to want to look at it or not, but there may be some missing pieces of the puzzle that you could find there. But I would only think that the A-plus student would be looking at a lot of that. Somebody who really likes R and figures, oh, I can use this in a career, which is definitely true, by the way. So this is a skill that you can use. It's something that I've kind of lived without for a while, but I'm a little bit older than most of you guys, so that's how that goes. And but yeah, this is a combination class, statistics and R. It's really both. So we have this idea of confidence intervals and their uses. And the way they explain it is not my favorite way, but we'll try to cut through the chase and I'll kind of sift through the best parts of 10.0. So they talk about sampling distributions. This is like taking a sample, taking another sample, taking another sample, like taking 100 samples of 100 people. That's 10,000 people. But you break it down, all these different samples. You see what their sample means are especially. And it says that we take a look at what the real mean would be, but yet if we take different samples, we see there's a spread of all the different means that are out there. And we'll take a look at that part. I like that part. The computer part is far easier than doing it by hand. So we sometimes have narrow sampling distributions with very consistent data, and our estimate will be very close. If it's off, and the spread out distribution will just not help our particular estimates and predictions at all. So that has to do with luck or the nature of the distribution that you happen to be looking at. But the idea of confidence intervals, and I have a PowerPoint that I think frankly is better than this. It's not as pretty looking, but I probably should just show you the PowerPoint. But anyway, maybe I'll see about doing that. But how far off could our estimate be? What are the edges of likelihood? How far can we go between particular numbers? So they suggest that maybe with 95% confidence, even though the mean was 60.1, we're going to put kind of like goalposts down. It could be as low as 58.7 and as high as 61.5. And we're going to say that around 95% of the time was what it should be. Now, it doesn't mean, here we go into the argument about does the Earth rotate around the sun or do all the planets rotate around the Earth, as they used to think 400, 500 years ago, till Galileo came along. But what we're really saying here, this same analogy for this sort of thing, the true mean will be contained within the confidence interval 95% of random samples that you could draw. So yeah, we're not saying that the true mean is definitely here. We're saying that the true mean would be contained within that 95% of the time. It's very similar. Do not worry about this for the test. It's a subtle distinction, but there are a few mistakes that could be made on a more advanced level especially. So I will not worry about that too much, but I do feel obligated to point it out. Basic logic between confidence intervals. Well, we did talk a little bit about it, but I did skip most of 7 and 8, so this is going to be a little bit of tying things together here. And feel free to look at the end of 7, the beginning of 8, anytime you want. I do not expect that any of that would be on the test, but then again, I didn't make it to the meeting. I had technical issues, so I've sent out emails, have not gotten responses, so I get the feeling things are still up in the air as far as coverage for the final. I will let you know as soon as possible, but I think that it would possibly cover the beginning of 7, the end of 8, and pretty much all of 10, along with the material from before. Okay, we have this idea of the true population mean. That's the Greek letter mu. It's a little m in Greek. We don't know what it is exactly, but it's out there somewhere. If you got the entire population, you'd eventually find it. Big samples tend to pin it down pretty well too. So here's a possible representation of reality. They call it a DGP. And they're saying that maybe the mu is really 60.1, a standard deviation about 8.7. And here is one of the sampling distributions. There's an infinite number of ways of sampling. And this is just one that would match what we are thinking maybe it is. Now, this happens to be, these are simulated means, but this is the actual data. So there's a difference here. This is the actual data that we got. This is all we have to go on. And our particular mean, they call it y bar, would be 60.1. So this would be a very convenient, almost too convenient situation. This is our best guess, but it's one of many, many, many possibilities. But the good news is they're finally going to get to is that it has to stay within a certain level, certain region. And they've kind of tipped their hand and give you some numbers here. And we'll just kind of see how we can get there. And why is it contained between 58.7 and 61.5? Why would it be bad to go outside of that range? Well, we'll talk about that a little bit. So we see our sample represented on the bottom in green. This is the actual sample. The estimate is in blue based on 60.1, so that's going to be what we got. And we're going to use our if thinking and assume for a moment one possible version of reality. We assume is normal, has a mean of 60.1, standard deviation of 8.73. So that's what this is. They're just saying what I just said, basically. And okay, let's take a look at some of these little questions here. And I think the magic letter for most of these is C. Does this figure prove our sample came from a population with a mu of 60.1? I wouldn't say absolutely, not quite. The figure shows that 60.1 is the most likely one, maybe, but this figure shows that a population with 60.1 could have generated our sample, and that's the more conservative way to do it. And you can say that for sure. B, very likely, but we're not completely sure. And A is just off, because we're not 100%, we're like 95% sure. We created this particular sampling distribution by simulation. We could have used the central limit theorem. So they go kind of really detailed into this sort of discussion, and certainly be sure to look at this. An important definition here, standard deviation of this sampling distribution, the blue zone, is called the standard error. Okay, so we'll take a simulation, which is certainly one way to do it. Then pretty soon they're going to simulate 1,000 variables and see what happens. Okay, the true mean, this gets rather confusing. I'm just trying to step my way through enough of this so you get a little bit out of it, and feel free to read for detail. This is just not the way I would set it up completely. We don't really know the mean of the population. That's difficult, usually impossible to find, unless you're willing to do a census, or if you have a small enough population, you can actually get everybody, which often does not happen. You can be virtually certain that this is wrong. So that's a very frustrating thing to say. I kind of wish they wouldn't say it that way, but it's true. That 60.1 was a best case scenario. It could be slightly to the left, could be slightly to the right. Odds are it's not going to be way over there, or it's not going to be way over there. So in other words, this question mark is very likely, but the other ones is not. The middle two look pretty good, but those others, especially that one, that's way away. I mean, it could happen, but that would indicate some sort of problem with the collection type of situation that we had going. Okay, as I try to wade through this stuff here, here's another example. What if the mu really was 57? Now we got a sample of 60.1. That would be off a little bit, but the question is, would that be acceptable? I'm afraid I don't think it would be. I think they listed 58 for reasons they have not explained yet as being a typical number. Get some more coffee here, excuse me. So that's another possible situation, another set of simulations. So if the true mean was really 57, then we would have said that our sample is kind of high for that 57. This is all what if now. On the other hand, if the true mean was 63, then our sample, which is not changing, they're keeping this same sample, they're moving the population mean around as a way of guessing. Now, normally you cannot move the population mean around, so it does seem a little crazy. But then the 60.1 would be kind of low. We'd have to say, oh, we must have a low sample if this is really true. So this is truth. This is what we have. Then we'd have to say, oh, we're a little low. Is it acceptable? Kind of no. So we slide this around. And they do some of this on the video. The video actually does a better job of explaining it than all the fancy diagrams do. So be sure to watch the video. I cannot play it for you, but she kind of gets more concise and hits her points much better on the video. So absolutely, watch the video as soon as you can. It's towards the end of this section. So anyway, they're saying that just as a start, they say that population mean, the true population mean, is probably between 57 and 63. These numbers seem to be a bit extreme, but for sure it should be in between. Maybe even something close to 60, 60.1. Narrow it down a little further. As I mentioned in another class, you can never have a 100% confidence interval. It's never going to happen because that would include all the numbers from minus infinity to plus infinity. Or if you talk about percentages from 0% to 100%. And that's just not going to happen. So the idea is to be correct as much as you can. Reasonably speaking, 95% seems to be the best balance of things. So what we're going to do is we're going to take the 95%, subtract it from 100, get 5%. We're going to cut the 5% in half and get 2.5%. Then this goes into a train of thought that they are trying to show you here. So if we look at a particular DGP, they have not given us a mean. It looks like it's around 61.5, and they cut it off at the lowest 2.5%. And I guess what they're trying to get at is that if you're at the tails, the lower 2.5%, the upper 2.5% are then considered to be unlikely, but the middle 95, that's the likely zone. I wish I could draw on the screen, but the likely zone will be in the middle. You'll see more graphs coming up here. So this is like the edge of what would be considered okay, and that shifts the mean over up to about 61.5 or so, and that would be considered to be all right. This is not the way I think of it, but it happens to be true. Not what they say is wrong. It's just emphasizing different things. So anyway, they go through more on that, and 60.1 is the one that gets you to the edge of 2.5. And they're going to do it on the other side too. They move it over to the left, maybe at around 58.6 or so, and they find that on that true distribution, the blue is what's supposed to really be happening, our sample in green, which is subordinate to the blue, so that has to be clearly understood. Our sample is not quite as important as a true mean. This is a guesstimate for the true mean, which is almost a contradiction. But they're looking at the 2.5% on the high side. So this sample would be considered to be rather high, which in turn bends back the sample mean, or the population mean here, all the way down to about 58.6. So that's where they kind of get their numbers from. Notice how the sample has not changed at all. Same number and all that. So what they've done is they've kind of slid back and forth and kind of pinpointed what they consider to be the middle 95%. Yeah, this is a way to do it. I'm more into working problems and getting the intricacies of what to do with various situations. But this is just a way of emphasizing a little bit of theory that they're very much impressed by. And certainly nothing wrong with it. So we're looking for sealing off the most extreme 2.5% on the left, sealing off the 2.5% on the right. We have a better picture coming up and a very good video here. The video is actually much better than this presentation is. So do not skip that, please. I'm assuming after very soon that you will have seen it, and then it'll make a little bit more sense if you do. I don't have the time to copy what she does. I'm kind of putting things in my own words, but you need to watch it. I cannot play it for you now, of course. Which of the three sampling distributions is unlikely to have produced our sample mean, represented by the blue line, because our sample mean, 60.1, would be too low to be likely. Well, it looks like C is the answer for just about everything. And this 67.5 is just too far over. That one is not going to be true. If we have reason to believe that the sample mean is 60.1, and then we say the true mean is 67.5, that's off by 7 units. That's too far over. Now, you might think that these are betas, actually not B's. They're betas, the Greek letter B. And that would be only off by about 4.5. So that's not too bad. It's getting bad, but it's still okay. But the 61 is almost right on top of the 60, so that's actually very good. So the only one that's terrible is 67.5. And then they say that it's too low, because then they say that suddenly our sample, the green stuff, has been moved to the left. If this is true, then that's moved to the left too far, and there's a disconnect there. You just have a different way of saying it. So C is the answer to that. The lower bound is the lowest number for which a confidence interval can be confident of success. If you go a little bit beyond that and suddenly it's unlikely and we vote against it. So this confidence interval is where we would say, yes, we think that this is still okay. And the way they do it, though, is a little bit different from what I'm accustomed to seeing, but that's all right. We see the logic. All we have to do is find the exact distance. So here's the part that I will not hold you responsible for. Absolutely not. This is a bit out there, and these people that teach the class have never even taught statistics before. They're more like programmers. I'm sure they will be rather befuddled by this. I had to look at this many times myself to figure it out. But essentially, you find the extreme distributions, which are really going to form our confidence intervals. And we kind of look how far it takes to get over to the sample mean. And they happen to call that the margin of error. I've seen the algebra works, and we had to work all that stuff out in my statistics masters. But yeah, this is just something that's kind of meant to be intuitive. Do not worry about this. Just take a look at it and think of it as kind of like trivia, because I'm not going to ask you questions on this, but we do want to talk about confidence intervals, though. So the bottom line is important. This middle stuff, I'm not so sure. So anyway, they talk about the left portion maybe is 58.7 or so, and this right portion with a mean of 61.6 or so. And they kind of meet in the middle, and that's where the 60.1 should be that we have for our sample mean. Those are called the margin of errors. And so this is the better picture. Taken together, we find our confidence interval here. The two distributions can overlap into one. I just go straight to this bottom distribution, and so was that red or orange? Looks like red. Those red lines form the confidence interval. That's the important thing. And they go on and on and on about this stuff. Anyway, I don't really feel like repeating what they have to say, but yeah, they just happen to overlap just fine. And that kind of then gives you kind of a ghost left distribution and a ghost right distribution. They're just barely okay. And they're using their R to really paint a very pretty picture. I like pictures, but this case, maybe the picture isn't worth 1,000 words. It's worth 1,000 difficult words. Usually pictures clarify things quite well. This time, not completely sure it does, but you know, if you think about it, it does start to make sense after a while. But I'm not going to hold you responsible for it. There's much bigger fish to fry, in my opinion. And my opinion may be wrong, but I'm just going to try to do. Okay, so if we knew the size of the margin of error, how would we find the upper bound? Well, the upper bound says that we have to add the margin of error to the sample mean. That's simply C. So take the sample mean and add something to it to get to the upper bound on the right side. That's all it is. And lower bound, same idea. Take the mean and subtract. So subtract the margin of error from the sample mean. That's clearly D. That's clearly D. So yeah, that's how we get to the lower part of it. To show you quickly here, the lower bound would be here. You've got your mean and your margin of error. Subtract them, and you wind up at the lower number. So subtraction is low and addition is the higher one. That's kind of basic. And yes, here they go again with the same old picture over and over and over. And yeah, those two ghost distributions make up the 95% confidence interval. Okay, so I'm used to just using a formula or a computer package or a calculator to do it. So let's move on and get into some real stuff and shrink it down. See if I can get to the next. Sometimes it doesn't let me go to the next one. Nope, I guess I'll have to go module at a time. So let's go into 10.1, partway into 10.1. Don't plan to cover a ton of it, but we do need to get our foot in the door since we have to average about 2 sections per lecture. I do want to have time for review, so that last lecture should be mostly review. So that's the important thing, because we've got holidays coming up, Thanksgiving holidays. Now 10.1, first part, finding the 95% confidence interval with simulation. This is very nice. I like this. So we'd like to construct it. And yeah, of course there are formulas, but they want to do it with a simulation. They just established that the sampling distribution of means, those little blue zones, centered around our sample mean, can be used to calculate the margin of error. Yeah, that's all wonderful and stuff. So they have an R command that does this. It's called SimSDOM, in other words, Simulated Sampling Distribution of Means. They're always coming up with cute abbreviations that I've never seen before after teaching this stuff for a few decades, I'll put it that way. This R code produces a data frame with 1,000 simulated sample means. And the mean of this should be very close to 60.1, which is our estimate. And so the computer will tell us what they feel that the confidence interval will be. Keep in mind, though, every time you run it for 1,000, it's going to be a little bit different. It'll tend to cluster in towards a settled number as you take several samples. But for now, they're going to try to find that. And to find the margin of error, let's find the range within which 95% of the sample means would lie. And we're going to assume that the mu is 60.1. So that's an assumption we're going to make. So we'd like to find the 2.5% that's on the low side and the 2.5% that are on the high side and cut them off. So that's the important thing. Cut off the low 2.5%, cut off the highest 2.5%. Very important to do that. Okay, so a simple way to do it is just to arrange our 1,000 simulated means in order. And so given that we simulated 1,000 of them, we figure, very easy to do, that 2.5% of 1,000 would be the lowest 25 means. Those are the ones that are considered to be too far over, too extreme to the left. Not talking politics here. Highest 25% would be too extreme to the right, the higher numbers. So we wouldn't want those. We want the ones in the middle, be in the center, the 95% in the center. That's the very definition of a 95% confidence interval. Okay, and yes, we just spelled out the fact that why are we interested in the lowest and highest 25 means? Well, there it is. 25 is 2.5% of 1,000. Now they have this arrange command that puts the means in descending order. So they apparently are using that, and we can try something with that ourselves. So I'm going to copy this because they'd like us to try it. And so here we go. As I copy and paste, put it down here. Let's see if I need to make any changes. Arrange what I'll call SimSDOM in descending order by mean. DESC is descending. So, okay, that's how that goes. And we can print this by talking with the head command, and that automatically gives us 6. And it's going to be this complicated name. Notice the different cases, uppercase, lowercase. So I'm going to copy that and put it inside the head command and copy, and then yes, it gives me the other parentheses immediately. Now something we haven't used very much, but the last 6 lines is called tail. Makes perfect sense, heads and tails on a coin. So let me put that in, and I will now go ahead and hit Command V to get that in there. Okay, so now we should be good to run it. Oh, the hint does say use the descending function to arrange in descending order. Let's go ahead and run it. And so we see the top means, and this is not in the usual order. I think ascending order will be the typical way to go. The first one could be the lowest one, but here the first one is actually the highest mean. We actually got a mean as high as 62.9, which is way ahead of the second highest one, by the way, which is very odd. And then the lowest ones could go as low as 57.67, let's say. And so I close this up. You can take a look at it. We've got a better look down here, so let's take a look at the bigger picture. And these are the top 6, high of 62.9, and the bottom 6, low of 57.552. Okay, so that's quite a range right there. These are each all sorted, all the means that they got. I guess 157 each time. So notice the means are in descending order, so you go down the column, the numbers get smaller You can go the other way and try it the other way if you'd rather, but this seems to be okay. When I find the cutoff point, we simply look for the 25th mean from the top. That will be the upper cutoff. And then the lower cutoff, do the same thing from the bottom. The 25th mean for the bottom, which, oh, by the way, 1,000 minus 25, 975. And we'll get to that in just a minute. So here is the R code that does that. You type in the name, $mean, because we want the mean, 25th value. That's what we'll want. So here we can talk about the fact we have 1,000 means in our sample. Which of these represents the lower cutoff, or the 25th mean from the bottom of the vector? Check all that apply. And 25 is actually wrong, because that'd be from the top. 75 is not even close. Here we go. In fact, let's look at D first, because we have 1,000 minus 25. That gets us to 975. And C and D are exactly the same. C is a bit more direct, but D tells you how we got there. And so the idea is to look at those bottom 25 and the upper 25 and see what we come up with, and basically reject those. So match the following labels to the corresponding part of the figure. Assume that the 1,000 means have already been arranged in descending order. So for part A, we see that that would be way over here, and remember it's in descending order. So that was number 1 here, number 1,000 over here. So going this way, A is actually the 975th mean. That's easy to mess up. It is going kind of backwards. They decided to go that way instead of a different way. But B would be the other one, and that's going to be the 25th, because if number 1's over here, the biggest of all, then this would be the 25th value that we have to start cutting off, and that's what B would be. And then C, notice C is not, both of these is only half of this confidence interval, kind of the left half of the confidence interval. So we'd start off with the value we had, which I believe was, let's see, yeah, that's simply the margin of error. And yeah, okay, so one thing that I probably didn't, because of all the stuff they were throwing at us, I didn't really explain very well. Margin of error is going to be half of the confidence interval. So we have that, and it goes from that number by 58 to about 60.1. So it is just a margin of error. There are 2 margin of errors inside a confidence interval. I see my battery is starting to die, so I'll have to wind this up pretty quickly here. But what we can do now is to get stuff going, and I think I'm going to copy this and see what we have down here. And the idea is to write code to print the 25th mean of that. So I think they've already kind of gave us a nice little head start here. So I'm going to copy this as well, change this over to 975, and now I'm going to run it. And there they are. These are the numbers that are just not considered good. These numbers are out of bounds. The top 25, the bottom 25 have those numbers. So they could use those numbers as the confidence intervals. Because everything inside this region between 58.695 and 61.474, those would be where we're confident. And you'll notice this is your 61.4 something, this is 58.695 something. So it does seem to correspond pretty well with all of that. Move the following labels to the corresponding part of the figure, and I'm going to have to kind of wind it up here. We have the fact that 58.7 is the first number. That would be A. That would be A, and let's see the figure. There it is, your A. And B would be 61.47, so that's an advantage there. And then C, once again, at half the confidence interval, would take us from the left edge to the middle. And the last one I'm going to get to do is A. We simulated this. Again, will we exactly the same numbers? No. Simulations will be different. That's going to be it because my battery is dying. I was pretty much done with what I wanted to say anyway, so that does not harm us in any way. Anyway, study hard, and we'll be live again on Wednesday, actually Thursday and the following Monday. So for the Monday, Wednesday group, Wednesday is recorded, and Monday is live. That's for a little while anyway. Okay, that's all I got. Have a nice day.